efficient. It allows to compute amplitudes of massless fields very efficiently and presents them in a very compact form. And also it combines well with other modern techniques like BCFW, CHY, etc. So this was about Flatspace, but there are also good reasons to compute amplitudes in ADS. One of these reasons, of course, is holography. And it would be nice to have equally efficient language for computing amplitudes of spinning fields in areas as well. So this is one of the motivations. And I don't know if you are a bit in this topic, maybe you've heard about another Spinor-helicity formalism for fields in areas by Maldacen and Pimentel. So what I'm going to explain is something a bit different. Okay, and another motivation, which is main for me, is comes from Higherspins. And like making a long story short, just to start, I would like to construct massless Higherspin theories in Flatspace. And I'm arguing that Spinor-helicity formalism is beneficial for these purposes. So let me start from kind of reviewing briefly the background on Higherspins, what kind of problems we are facing. So the first thing is that, well, there are Higherspin theories in areas. You can construct them different ways. I prefer the one which extract them using holography. And well, one can argue about like different definitions of locality, etc., etc. We could hear that, say, in the talk by Misha Vasilyev. But like if you take the standard definition of locality, then Higherspin theories in areas are not local. Similar situation takes place in Flatspace. So there are numerous no-go theorems saying that essentially Higherspin fields cannot interact in Flatspace. And the main assumption which prevents that is locality. So let me emphasize, like explain what's the role of locality. First, clearly, this is a necessary consistency principle for having reasonable physics. That's why we just cannot just drop it, right? Another thing is that locality is, we use it in practice when construct Higherspin theories. Namely, we usually start from free theory, then we add interactions order by order and ensure consistency. And the thing is that if you drop any requirements of locality, this procedure becomes empty. That is, you can write essentially whatever you want. So from this like point of view, locality is important. Otherwise, well, we cannot construct anything meaningful. So as I said, it seems that locality, despite we need it, it seems that it's not there in Higherspin case. So one can think of like, what can we do if we relax locality? So apparently we need something that would replace it, like in its various roles. So one of these roles is that this new principle should ensure consistency. Another is that it should be somehow constructive and allowed to produce Higherspin theories. And this is not entirely new, so you should not be too surprised. Sometimes something like that does happen. So here I give some examples. One example is string theory, which is when rewritten as string field theory is non-local. Still, we are happy with the result because there is a worldsheet construction which ensures the consistency. Another example is Higherspin theories in areas, which, as I said, are non-local, but still there is a holographic description in terms of free CFTs or like ON vector models on the boundary, which are perfectly fine theories. So it should be fine in the bulk as well. So what can we do then in Flatspace? Well, the suggestion is very simple. We just consider some sort of a flat limit. So in this respect, my talk, like conceptually is similar to other talks that we had here, for example, by Andrea, Daniel, and Stefan. The difference is that I will be focusing mainly on like amplitudes, like not algebras, but amplitudes. And yeah, once we construct these amplitudes, like returning to the previous slide, we can expect probably that there is some holographic underlying construction that would ensure consistency. Yes, and so I will explain later that it turns out that Spinor-helicity formalism is beneficial for this analysis. So let me now go into more details. to explain why Spinor-helicity formalism is useful in this context. So first, there are Higherspin theories in ADS, and one way to construct them that I like the most is to extract them from holography, which means that probably you know that there is this holographic duality, and Higherspin is one part of it. Another part is ON vector models on the boundary of ADS. And so one can do the following. You assume that holography holds, right? Then you have correlators on the boundary, and then using holography, you just reconstruct interactions of Higherspin fields perturbatively order by order. So this was carried out in practice. Here you see some references. Yes, and conclusion, as I said, is that, well, at least in the standard sense of this kind of term, the theory is non-local. But then there is another development which is completely independent. You go to Flatspace, then you fix the light cone gauge. Okay, let me just stress that all this is in 4D, so and like whatever follows. So you go to flat 4D space, you fix the light cone gauge, and then you try to construct interactions perturbatively. Then there is a well-established procedure how to do that. There are some consistency conditions to solve. You solve them, and as an outcome, you find what's called chiral Higherspin theory. So there are some nice features about these theories. Well, in fact, there is a family of theories. So first is that they involve only cubic interactions. Then these theories are perfectly local. And another, like, probably statement that characterizes them best is that they can be regarded as very straightforward generalizations of self-dual Young-Mills and self-dual gravity to Higherspins. So you could see some details on that in talks by Kirill Krasnov and Zhenya Skvortsov. The important thing here is that the light cone approach allows to construct additional interactions which are not available in terms of Fronsdal fields. And these vertices are in fact important because they enter this theory. They are unavoidable in these theories. Yeah, which highlights importance of using light cone approach compared to the usual approach which deals with Fronsdal fields. And it turns out that Spinor-helicity formalism, which I'm going to explain in the following, is closely related to the light cone formalism, so it also features these additional vertices. But Spinor-helicity formalism for many purposes is by far more efficient. That's why I'm going to focus on it. And then let me also stress that spinors are also used extensively in Vasiliev theory. So yeah, the role of spinors for the Higherspin theories yeah, is sort of clear for some time. Okay, so we had a sort of self-dual Higherspin theory. What we want to do next, we want to construct its parity invariant completion, something like what is Young-Mills to self-dual Young-Mills. So we want to construct a parity invariant completion of a chiral theory. And the analysis shows that it's impossible unless you do something non-local, which is perfectly consistent with what I said before, no-go results. However, there is an interesting observation, and it consists in the following. So if you start from holographic theories, and you consider some, like, in quotes, flat limit, then cubic action of holographic theories reproduces cubic action of chiral theories in the certain sector. Okay, so these are apparently not related theories constructed in absolutely different ways. It seems that these are closely related. So let me now explain a bit. Yeah.
May I ask that this putative parity invariant completion of chiral Higherspin theories is supposed to be unitary or non-unitary?
Parity invariant condition?
Yeah, so you would like to reconstruct, thanks to non-localities, a unitary theory, or you are still working without caring about unitarity?
So I would like to mimic like the way how it works for Young-Mills and self-dual Young-Mills. So self-dual Young-Mills is just in a way part of a complete Young-Mills. Young-Mills is unitary. And I want to do something like here. I regard this chiral Higherspin theory as just a piece, and I want to complete it to a unitary theory. Okay. So let me now explain what I mean by all this. Oops, there is something wrong with the slides. Or no, there are some slides missing. Right. So what I will stop sharing now and share a different file. Yeah, for some reason.
So conference dinner was a success, apparently.
So can you see this, right? Okay. So I wanted to explain yeah, what I understand by flat limit. So I took it in quotes. So let me explain what this means. So you could hear like many times that flat space limit in Higherspin theories doesn't exist. And indeed, this is true if you do it naively. By this, I mean the following, that in Higherspin theory, in ADS, every derivative comes together with the radius of ADS. You can just see that on dimensional grounds. And so for spins S1, S2, S3, the vertex looks schematically as indicated there. So you have a powers in derivatives. It starts from a derivative S1 plus S2 plus S3, and then a number of derivatives drops for every term by 2. So if you just take R to infinity, clearly this thing blows up. Every term blows up. But you can do something different. So it was first suggested here. You can take each vertex and rescale it with, well, with some overall factor. By this, you introduce this additional dimensional parameter L. So you just rescale each vertex separately with different factor. And then here you can see that if you take the flat space limit, then just these terms disappear. Then covariant derivatives get replaced by partial derivatives, and you get a vertex which also turns out to be a consistent cubic vertex in flat space. So I should note here that, well, for any fixed triplet of spins, S1, S2, S3, there are in fact 2 different vertices in 4D. And as you can see in this procedure, only the highest derivative vertex survives, which means that, well, we lose some information about the vertex, which doesn't seem to be good. But still, like in these papers, it was suggested to check this matching between ADS and flat space theories in the late quant using this kind of a limit. And the matching was indeed observed and holds in the highest derivative sector. But one can do something.
About this scaling. So if you have a single vertex, I understand. Suppose that you have all the vertices, let's say for each copy of each spin.
Yeah.
So how do you define this procedure? You rescale a given tensor of rank S with a given factor?
Not each tensor separately, but each vertex separately. So again, this here I'm talking only about cubic interactions.
Cubic. Let's talk about
each cubic vertex with fixed spins.
Yes.
You rescale with a different factor.
Okay, so what is the systematic of the procedure?
No, there is no systematic, but I just want to say that this actually works.
Yes, I understand, but I would say it's not so fully convincing to show that the flat limit exists. Because if you cannot define a rescaling that holds for a given field in all vertices, it seems a little bit too ad hoc, no?
Well, so I agree that there is a problem of the following type, namely that consistency of the original theory does not ensure consistency of this, right? Because you do something out of code. But the procedure is well defined, and yeah, it seems that it gives good results. Yes, yeah, in this sense. So we can try to do something even better. So when we are using other approaches like light cone or Spinor-helicity, each spin corresponds to two helicities, which makes this labeling of vertices even more refined. So like instead of spin S, you have helicities plus S and minus S. And then for a fixed triplet of helicities, you get a single vertex. And then you rescale each of them in a similar way with different coupling, with different prefactor. Along the lines of the previous slide, then you take a flat space limit and then everything survives. So the expectation is that there is a matching between the ADS theory, the one which is derived holographically, and the flat space one, once you do this type of a limit. And there are indications that this is indeed true, but it was done in the light cone and not by taking the limit from holography, but rather studying consistency condition in the light cone in flat space and in ADS. Okay, so then the natural suggestion is that we just extend this procedure. We go further. We don't focus only like on the spiral part. We consider parity invariant theory, and then we go beyond cubic order. And it would be interesting to look what we get if we use this kind of flat limit. And then, of course, since the right-hand side has underlying holographic construction, one can expect that there is also some holographic construction on the left-hand side. Okay, so as I mentioned, flat space holography, I know that there are many experts in this field, and there are many efforts put into it. And so yeah, the subject is quite complicated. So as I understand this, that despite significant effort, thus far, there is no dual pair proposed. And if we are trying to do something to make progress in this direction, it seems that Higherspin fields is the first place to start, because as you know, at least in the ADS case, it's the simplest example of the duality. Okay, so here I'm giving more precise kind of problems that I will address in this talk. So essentially they split in two parts. The first part is just developing Spinor-helicity formalism for amplitudes in ADS. So just to explain what this problem is. There is a huge bulk of work on Witten diagrams, so you can compute them in different approaches. And here we essentially have to do the same, redo all this analysis, but in a different representation. So I'm not going to redo everything, but I will just focus on key features, which are important for the following, namely on 3-point amplitudes. And another part is more about holography. So I will be talking about how you can extend this approach to the boundary. So are there any questions so far? Yeah.
So when you complete the spiral theory to parity invariant theory, it's presumably non-local, right?
Yeah, it should be inevitably.
From the Flatspace limit, you get local vertices?
No, it's still non-local, but as I said, we need somehow to justify why we can do something non-local. And I think kind of flat space holography would be one, would be a good justification. Okay, so now I'm going to review the Spinor-helicity formalism in flat space. So there are basically two key ideas. The first one is that there are only two numbers, quantum numbers, that we have to specify to describe a state which appears on the external lines of a massless particle in 4D, which is just momentum and helicity. So momentum squares to 0 and helicity is half integer. And the idea is that if you just keep this physical information and remove any redundant information, and write your amplitudes in these terms, then they can be compact, very compact. So you don't have to introduce any kind of this polarization vectors, gauge invariance as you usually do. You just keep the relevant information. And the second idea is, as I said, very like typical in 4D. It is convenient to use SL2C spinors. So there is isomorphism between the algebras. At Lorentz group SO3, 1 is the same as SL2C. And this is convenient because in these terms, momentum squared can be solved. And P alpha alpha dot is a product of lambda alpha and lambda alpha dot, which are just SL2C spinors. So this is the way how we are going to encode massless momenta. And concerning helicity, so the statement is that the wave function has fixed helicity h if this operator gives a definite value h acting on it. So you can see that it just computes some homogeneity degrees in spinors, so it's pretty simple. Okay, so if you want to do Feynman rules, we of course we need plane wave solution, something to put on the external lines. And in Spinor-helicity formalism, it works as follows. So this is the field strength. It's like dual or self-dual or anti-self-dual part in spinor notations. So you would see something like that in Vasilyev lectures. So it has two H indices, and these two H indices are saturated by these barred spinors, SL2C spinors. And here you have a simple, it's just a usual exponent of IPX converted to spinor notations. So this is the field strength. Once we know the field strength, we can construct potentials. This is done not in a unique way, of course, because there is gauge invariance. But in the Spinor-helicity formalism, this gauge invariance is fixed in some particular way. So you have these polarization vectors, which are given in a very specific form. And let me comment a bit on this form. So here you have lambda and lambda bar, right? So I explained what this is. And these mu's are auxiliary spinors. And one can check that if you contract this auxiliary spinor, contract this polarization vector with auxiliary spinor, this thing, the product vanishes. So this is some sort of a gauge which is transfers to mu, this auxiliary spinor mu. And well, as it's an auxiliary spinor, and one may wonder what happens if we take another one. And what happens is that you just perform a gauge transformation. So you're free to choose any of them. And usually in computations, one chooses these mu's in a way that computations simplify, and there are some systematics how to do that. Yes, okay. And okay, then you have these plane waves for external lines. You plug them into the usual Feynman rules, you do calculations, and at the end of the day, you find something like this. So you have this type of an expression. Okay, I'm going to comment on its pieces. So this is just a momentum conserving delta function, which is a consequence of translation invariance. So usually people don't add it inside amplitude, but I will keep it because it will help me to make contact with the ADS case. Then you have also this prefactor, which is expressed in terms of this angle and squared brackets. So this angle bracket is nothing but the contraction of two spinors with SL2C invariant metric, which is just antisymmetric tensor, and the same for barred spinors. Then auxiliary spinors mu drop out. Indeed, there are no mu's, and this is the consequence of gauge invariance. And finally, like if you specify helicities of fields on external lines, well, as I said, this requires that homogeneity degrees in spinors are fixed, and you can check, like looking at that formula, that this prefactor does have the correct homogeneity degrees.
It doesn't know if it comes from a local or a non-local. It's amplitude result. It doesn't know if it comes from a local or non-local action, or does it?
So this one comes from a Young-Mills theory.
Okay, but in general,
well, immediately it's not clear. So there are some kind of things like you can look at how it factorizes. Oh, there are many, okay, I'll put like that. There are many constraints on how this amplitude should look like besides just symmetry considerations. So like an amplitude should factorize on the poles and produce a product of sub amplitudes. So there are many requirements like that, and this ensures locality. this amplitude satisfies this property, but it's not immediately seen. You should study it. Okay, so if we just use these symmetry arguments from the previous slide and apply them to the three-point amplitudes, then we find that they fix. Okay, I'm omitting some subtleties, but roughly speaking, you fix three-point amplitude for spinning fields up to a prefactor. And it has a very simple form. So you have a momentum conserving delta function, which is not surprising. And then you have these brackets, and their powers are fixed by requirements that helicities are right. And you have similar things for squared brackets. So let me now explain about additional vertices. So we can look at the particular case, spin S, spin S, spin 2, a cubic interaction. And so these spins, S2, correspond to helicities, so you can change signs. So there are different configurations, plus S plus S plus 2, plus S plus S minus 2, plus S minus S plus 2. And then there is a simple rule that each pair of spinners corresponds to one derivative in the action. I think it's easy to believe that if we remember that P is something like lambda lambda bar. So pair of spinners gives one derivative. Yeah, and now we do this counting for these three amplitudes. So yeah, and it's not hard to see. Okay, it's just very simple exercise that the first amplitude has 2s plus 2 derivatives, second one 2s minus 2 derivatives, and the last one 2 derivatives. And the point is that the amplitude with 2 derivatives cannot be constructed in terms of Fronsdal fields. If we use standard rules, let's say, that we don't like violate locality or don't do something weird with tensor indices, etc., etc. And well, another curious thing is that this two-derivative vertex is something that we would normally associate with the minimal coupling to gravity. So you might have heard that there is no minimal coupling of higher spins to gravity. This is the case only if you work in the Fronsdal formulation. If you do Spinor-helicity or light-cone-gauge, these vertices are actually present. And well, another thing is that, well, you might have heard that in high spin theories, number of derivatives grows with spin. Again, this is true for Fronsdal formulation, and this can be different in the Spinor-helicity formalism and light cone. So some remarks on that, like on Spinor-helicity, like before we are finishing with Flatspace, is that it works well with other methods, and there is a rigorous way to relate it to light cone approach. So essentially, these are two different approaches. One is the official version of another. So how much time do I have?
Half an hour, 25 minutes.
Oh, okay, okay, I see. Okay, so we are going to Spinor-helicity in ADS. So many things we are going to keep. So this is how SL2C naturally acts. So this is the same as it was in Flatspace. This piece is the way how translations acted in Flatspace. And here what we do, we add this term. And the claim is that these commutation relations, they give us a 3,2. And moreover, the resulting representations are massless. And this result is very well known. So these representations are extensively used in Vasiliev theory, and also they appear one way or another in twistor literature. So we add this deformation, and now we want to see the consequences. The consequences at the level of plane waves for field strengths is the following. We just get this extra factor. So yeah, when doing this, we are using stereographic coordinates. And this thing is nothing but the conformal factor of ADS in stereographic coordinates. So the modification when we go to ADS is very simple. We just get some power of this factor. Okay, so once we have field strengths, we want to consider potentials. So for general spin, it's tedious, but here I give a result for helicity plus 2. Again, the solution is not unique because you have gauge invariance. And you fix it in a similar manner as we did it in Flatspace. That is, we introduce an auxiliary spinor mu, and we require that the potential is transferred to transfers to that auxiliary spinor mu. So things here get a bit more complicated. Just to compare with the Flatspace result, there you had only this one multiplying the rest, so this exponent and this factors pairing spinor indices. Everything else is extra. So here B and A are pretty simple things. So B is essentially just x squared, coordinate squared, and A is just P times X in essence. And on top of that, we have some extra structure where mu and lambda are contracted through X. And then having these potentials, you can construct amplitudes, compute amplitudes using the standard Feynman rules. This goes pretty much the same way, except, well, as you can see, it gets a bit more complicated because you have some additional X dependence. But conceptually, it remains the same. Okay, once you do that, once you compute these amplitudes, what you find is the following. So in the 3-point case, the amplitude looks as this. So again, the only difference compared to the flat space case is that you have this conformal factor, which was Fourier transformed, raised to the certain power. Yeah, so it's pretty simple. So you can reach this result either by computing amplitudes from the action or studying symmetries. So as I explained in flat space, you can construct 3-point amplitudes by symmetries. Here you can do the same. And so you get this result. And so at the end of the day, you see that the vertices look very similar to flat space. Classification is the same, which means that in particular, there are additional vertices in area space as well. Okay.
Because in ADS, you have like minimal covering to gravity in a sense. What do you mean by that?
So if you just compare the number of vertices you can construct in area space using frontal population with number of vertices you can do in light in areas, and in this approach, you get more and more vertices in areas.
Can you give me an example of a vertex that you don't see in ADS frontal?
Well, like SS2. SS2 was two derivatives. So as I explained in flat space, for example. For example, this one, where you take for H1S, for H2 minus S, and for H3, say 2. Then you get something which is supposed to come from vertices to derivatives only.
So not entering the ADS tail.
Yeah. So the difference is that in areas you have vertices which have like many derivatives, the leading term, and then there is a tail with lower derivatives. I assume that this kind of vertex would correspond, it would also to write to a vertex in frontal terms. The vertex that starts with two derivatives and then probably has terms here. But it's impossible to write.
So and then I close. It's kind of your expectation conjecture, or you can really.
No, you just count how many of them you have in one approach and in the other, and there is more in this one. And this also refers, of course, to CFT correlators. So on the CFT side, you construct correlators and construct parents, and well, there is a classification, but this is essentially the same. And there are, which means if you use this approach, you get new 3-point correlators for construct parents. Some remarks, so just on the relation to the literature. In the twister community, people also have like their own twister methods to compute amplitudes in areas, and they computed it in some theories, and the amplitudes appear to be in the same form. So you also have the same factors, conformal factors. So this thing I said already, and these results agree with the results of Mitsayev in the light cone gauge. finally, I want to emphasize that, well, these computations are nothing but computations of Witten diagrams, just we use the different bases for plane waves. So at the end of the day, you can start from a Witten diagram and do some sort of a like integral transform, some like sort of like Fourier transform, and get from one representation to another. So it's not something like very special or something that you don't know. Any questions? Okay, now I want to, I finished with the bulk part. Now I want to discuss a bit Higherspin holography and what happens on the boundary side. And I will start from quickly reviewing things. Higherspin theory is a part of holographic conjecture. So if we are talking about ADS for CFT3, then on the boundary side, we have ON vector models. And the simplest of them is just a free theory, which means that we have scalars, massless scalars, which additionally carry labels of ON vector representation. So this is the action. So since the theory is free, you have infinitely many conserved currents, which are supposed to identify it with bulk massless fields. And then holography says that you can compute correlators on the bulk side, on the boundary side, and these should be identified with amplitudes in the bulk. Okay, so the basis for this conjecture, at least in the simplest case of free theory, comes from representation theory, so it's just as simple as that. Namely, there is a statement by Flatter and Fronzel that the tensor product of two boundary scalars gives a sum of representations that can be identified as massless fields, massless Higherspin fields in the bulk. So you get an infinite family. So the boundary theory is free, which means that correlators are essentially computed using weak contractions. So it's very easy to do that. So the only thing that I would like to do, so conceptually it's very simple and it has been done like many times. The only thing that I want to do computation of these correlators in a suitable representation so that I would be able to match the correlators that I get with the results that I computed before in the bulk. Yes, so this is the goal. Yes, and so what that means? That means that we should design some sort of approach for fields on the boundary that would be adapted to Spinor-helicity in the bulk that I used before. So of course one can debate what this approach is, but I will suggest something, and well, everyone is free to judge whether it's good or not. So instead of just describing like a single representation, which is a massless field, I want to be a bit more general. I want to describe all conformal fields on the boundary in 3D, which means that there is some kind of a tensor field, and there is some operator of this form which acts on it. So you have this form of wave equation. So the reason why I want to do this is because I sort of want to kind of test tools to see whether kind of, I want to classify all representations of this type and match them with the existing results. And the idea behind that is that I'm trying kind of to find new opportunities for flat space singletons, for flat holography. And before doing that, I want to see whether I can reproduce all things that are already known in area space. Yeah, so I'm going to do that. And what I'm going to call the Spinor-helicity formalism for boundary fields, essentially it's very simple. I want just to keep SL2C symmetry manifest. So as it was before, SL2C symmetry was manifest. I still want to keep it and do it by utilizing Lorentz spinors. Okay. So to do that, I need some results from representation theory of SL2C or SL31. But luckily, Mark already explained this yesterday, right? But he used slightly different language. So here, like the outcome is the same, but the language is a bit different. So it turns out that you can realize all these representations using functions of lambda lambda bar, which are, so here comma should be omitted, which are additionally, which have fixed homogeneity degrees in these lambda and lambda bars. So here you have 2 powers n and n bar, and these n and n bar can in principle be complex numbers, and well, they're independent, but if you are more rigorous, their difference should be an integer number, because otherwise these functions are not single valued. Essentially, representations are characterized by a pair n and n bar, with their difference being an integer number. And you can see, if you remember what was yesterday, that it matches essentially the classification that was discussed. Another thing is that, well, if you take n and bar to be some specific values like integer ones, then these spaces of homogeneous functions, they contain polynomials, right? And clearly polynomials by these SL2C rotations go into polynomials. So there are these finite dimensional representations inside these infinite dimensional ones. One, of course, can factor them out. But in the following, we'll be mostly interested in infinite dimensional representations. Well, as before, Lorentz transformations, they act naturally. So this. So once we fix how Lorentz transformations act, we look at the way how deformed translations act. And here I'm just making the most general ansatz, which is consistent with the fact that this P should be a vector with respect to SL2C, which means that it has to have 2 indices alpha and alpha dot. And you can see that each term indeed carries 1 alpha index and 1 alpha dot. And this is the most general ansatz. And here functions A of n and n bars are still arbitrary functions that have to be fixed in the following. So something that I wanted to comment on is that, well, you can notice that each of these terms changes homogeneity degree in lambda and lambda bar, which means that if we start from, if we apply this operator to some representation of SL2C with fixed weights n and n bar, after that, these weights get shifted, right? And this term shifts them in some other way, which means that, like, if we start from a single weight, apply this P many times, eventually we get some sort of a lattice in the weight space lattice of SL2C weights. So this is, yeah, some sort of idea how our states on which the representation X look like. And the only thing that remains to fix is that these deformed translations compute appropriately. So we have to impose this commutation relation, and this commutation relation is what fixes for us these values A, B, C, and D, these functions. So we get some constraints and we have to solve this. So before going there, let me, yeah.
You can fix all 4 with the commutator, all 4, A, B, C, and D.
All 4, yes. Yeah. Well, if you like look at that carefully, so you plug this P alpha compute, let's say the left-hand side, then you'll see that it will have different types of structures. Okay, just a simple explanation. So you can see that you have this term applied twice, which shifts weights of lambda and lambda alpha of a bar by 2. And so there are other terms that shift these weights in different ways. So each of them has to be imposed independently. So you have many equations. Okay, for those of you who is familiar with unfolding, it might seem similar, and indeed it's very similar. So here I just want to stress the differences. So the important difference is the following. So in the unfolding, what one does is that you start from some infinite dimensional representation that you are interested in, let's say of the Poincare algebra or of the area isometry algebra, and then you decompose it into infinitely many finite dimensional representations. So into infinitely many Lorentz tensors. That's what you usually do in unfolding. But here, what we will do eventually is that we will start from a representation of SO3, 2, and we'll decompose it into a finite sum of infinite dimensional representations of SO3,1. So there are reasons why we have to do this. In fact, I have time to explain this. So this is just related to the fact that these modules are in fact short, and there are famous theorems by like Fronsel and collaborators, is that singleton representation of SO3,2 upon reduction to Lorentz Poincare up to Lorentz SO3,1, SO2,2, and ISO2,1. Upon this reduction, it remains reducible. But in more complicated cases, like for more complicated fields, we will get just finite numbers of them. So it's more natural to use finite expansion in terms of infinite dimensional reps rather than infinite sums of finite reps of Lorentz. And another feature is that when you have an infinite expansion, then it's harder to control things like unitarity. So here we have finitely many representations. Let's say if each of them is unitary and P's that makes them are realized in a unitary way, then we can claim that the result is unitary as well. So there are some advantages in doing this. Okay, I'm just giving the results of that analysis. So the solutions of those consistency conditions can be labeled by two natural numbers I and j, which add up to an odd number. So here I give a picture for the case I equals 3 and j equals 2. You have these filled circles. So this is the weight space of SL to C. So here you have n and n bar, which are weights of SL to C. And your weight space consists of this kind of lattice with 6 weights. And empty circles correspond to the case I equals 2 and j equals 3. So you have another rectangle that looks like this. So thus far, it was just like a simple parameterization of all solutions that we found. But of course, we want to connect it with some kind of standard and kind of labeling that people can understand what it means. And one of the way of doing this labeling is in terms of lowest weight energies and spins, which are just conformal dimension and spin in the CFT language. And the connection between these languages, between IJ and this conformal dimension and spin, is very simple. It's just a linear relation. Okay, so once we have this classification, we can compare it with those existing in the literature. So I use this paper for a reference, and it turns out that in bosonic case in 3D, you have like this family of Lagrangians. And in bosonic case, indeed, like if you can simply match the parameters. So for each spin, you can have any number of boxes in the section, and there is a matching between dimensions. But in the fermionic case, well, we just extend this classification to the fermionic case. Okay, let me explain you, just give more explicitly how this representation is realized in the simplest case of a scalar singleton. So in this case, we only have two weights in the weight space, which have homogeneity degrees. So this n and n bar, they're equal to -3/2 here, and -1/2 both for the second weight space, which means that our states are realized by functions, each, well, first one having homogeneity degrees -3/2 on both spinors, and the other one having homogeneity degrees equal to -1/2. And the translation, the form translations act in the following way. So you have, they act on this function with lower homogeneity degrees by raising them by 1. And here by differentiating this f, which decreases homogeneity degrees. And thus, like, it maps, this operator maps f -1/2 -1/2 to f -3/2 -3/2 in the opposite way for the other thing. Okay, and the relation with the radius of ADS is, well, simple. Is A times B equals -4/r². So this is what we have to impose for consistency. And finally, what I want to consider, so as I said, I'm interested in flat holography. So I would like to go into the flat space limit. And then it's easy to see, like looking at the formulas from the previous slide, that P times P is proportional to A times B, which should be equal to -4/r².
When we talk about flat limit of singleton, you think of singleton as a field on ADS.
I'm thinking of it as a representation.
What are so
it's just
a representation of conformal groups, and we don't have radius.
Okay, so for me, it's just parameters, so you commutation relations in the algebra. So you have P times P, which is proportional to 1/r. Right?
So in some sense, you like branch of.
Well, if you don't have R, you can reintroduce it by just getting P's. Right? So I agree that probably, like, from the point of view of the boundary, is not very natural notion, but we also discussed it like in previous talks. So it has the meaning of a Carolian, right? Carolian contraction. So you see the product of two p's goes to 0, which means that the action of translations is presented in an nilpotent manner. And this somehow is reminiscent of what Andrea explained to us yesterday. And well, it's not new. So well, in the original paper by Flat and Fronsdal, you can find statements that this should be the case. But I want to kind of stress that this already means that holography in flat space, at least if we take this as a singleton, cannot work. And the argument is very simple. So for singletons, translations are represented in a nilpotent manner. If we just take their tensor product, then for tensor product, they are still realized in a nilpotent manner, which is not the case for massless fields. So it definitely doesn't work the same way as in AES. Moreover, what I want to say is that this seems to be the general feature of flat space holography. Let me explain a bit. So there is a classification of unitary reducible representations by Wigner. What we want to look at, representations that could be identified as fields on the boundary, like on the scry. And these fields, so they are sitting on the three-dimensional space, and they're also subjected to one equation of motion. So they should be labeled, the states, by functions of two numbers, right, of two variables. This is what mathematicians called Gelfand-Kirillov dimension. So if you look at this classification by Wigner, then among unitary ones, those which have Gelfand-Kirillov dimension equal to 2, they all have translations realized 3 value. Which means that if you are trying to proceed the same way as you do in usual holography in areas, that is, you start from some fields, fundamental fields on the boundary, and out of them you cook up some like single trace operators to be identified with fields in the boundary, this cannot work because these single trace operators necessarily have translations realized 3 value, which is not the case for the bulk. So here I'm just speculating what can be the way out. And well, clearly one should somehow go around the Wigner classification. And as I said, Wigner classification refers to unitary representations only. So if translations are represented, if they are complex, they give complex numbers, then clearly representation is non-unitary. So the suggestion is to consider complex momenta, and this trick is often used in the ambient literature. In fact, it allows to make scattering of 3-point scattering of massless fields non-trivial. And well, one may expect that the same trick can be helpful in making this singleton representation also degenerate. And there was another suggestion in the literature by Per and Carlo to replace tensor product with something else, but well, they did not elaborate much on this, but probably this is still an option.
We did something else. It was really more.
Well, it's a tricky thing.
What do you mean?
No, unfortunately, we don't have anyone on. So there was some formula, but I cannot reproduce it. Well, some operation where you construct space of what would be massless Higherspins out of space of singletons, which is not just tensor products. But I don't know whether, like, to what extent it's consistent with everything that we want.
So the products with some weights, I mean, weighted way to act on it, this kind of field of concept.
There was some things like very skewed in like different spinors. Okay, we can take a look.
Okay, we can
there was just a single footnote. So they didn't okay, so let me just start from results that I want to highlight. Using Spinor-helicity formalism, one can construct additional 3-point amplitudes in flat space and in ADS in 4D, which implies that also you can construct additional correlators of conserved currents in CFT3. Well, then Spinor-helicity formalism allows to compute amplitudes efficiently in ADS4 as well. The difference with flat space is that you get some mixtures, the mixtures of X dependence because momentum is not conserved. But conceptually it remains the same, Spinor algebra remains the same. And we were doing some first steps towards rephrasing holography in this language. In particular, singletons were reformulated in a suitable way, and moreover, classification of all 3D conformal fields were obtained. So some future directions. Well, I would like to proceed, as I explained at the very beginning, what the program is. I would like to proceed with constructing, well, first rephrasing holography in areas in this language, and then taking its flat limit. So irrespectively of whether holography exists or not, I suggested before that there is some kind of a procedure, well-defined procedure how this limit should be taken. It's not clear whether the result is going to be consistent or not, but we will see. But well, irrespectively of whether it's successful or not, it seems that even if it's successful, this picture is somewhat incomplete without flat singleton. And it would be interesting to think how one can kind of expand the framework so that a suitable singleton representation do occur. Okay, thank you.
Thank you very much. Other questions?
So, it's very natural to try to find an analog of a flat space singleton, but somehow Higherspin holography, sorry, flat space holography, it's a bit unclear if it must be unitary, no? Because you have, say, gravitational waves that arrives at Scry. You try to do flat space holography on Scry, it looks like a sort of non-isolated system, you know, with these dissipative processes. So in this sense,
so what kind of dissipative process do you mean?
The fact that somehow you can change the energy that you have at Scry because there is a gravitational waves that arise, and
what's here compared to ADS space?
in the case of ADS space, you need unitarity because you have an isolated system in a sense. Also.
You mean they don't reach ADS massless fields?
The wall boundary of a de Sitter is a sort of, it's the analog of space like infinity in flat space. And so you fix what is going to happen there and you determine what is going to happen in the bulk. There it's slightly different physically because you have, it's a bit unclear, no? If the correct way is to have a system that encodes all possible gravitational waves that arrive, so if you just play with something that is non-unitary because at some point you can lose or gain energy.
Mm-hmm. Yeah, okay, maybe this is an explanation, but yeah. So my approach is kind of purely mathematical, so I'm taking just the simple structure that is there, and the approach of theorem, and I want to see whether it can be extended.
Just to say that maybe it's a context in which, I mean, unitarity may not be a theory that is unitary in the bulk may not require necessarily to have be associated to a unitary theory on the boundary. So although even my perspective shifted there, but I'm a bit more open to this fact because it's kind of different with respect to the usual ones. And there have been even some proposals for this dissipative holography in anti-de Sitter, so you can change the boundary conditions on anti-de Sitter in such a way to have loss of information also in anti-de Sitter. There, I'm not sure that the singleton plays the same role.
Okay. Yeah, it's a possibility.
Questions?
More of a general thought. Have you thought about ending your approach to BCFW for PDEs, since you're willing to go to complex momentum?
Extension to what?
BCFW-like constructions for higher point amplitudes.
No, there are many things that one can try to extend to it. Yes. Yeah, I didn't mention them, but we studied, let's say, analytic structure of amplitude. So, doing BCFW, you should first understand how, like, amplitudes and analyticity work exchanges. Let's say they're similar, complex diagrams, they're kind of analytic and things like that. So we were doing something a bit along those lines. We like computed complex diagrams, like classified all of them. So indeed, they have some kind of explicit clear analytic structure, but we should work along the lines, yes.
The reason why I ask is because then if you try to take a flat space limit, maybe there is an obstruction because these analyticity properties.
Sorry, why there should be an obstruction?
Because it's essentially non-local, right? When you try to make 4-point amplitudes or something, 4-point amplitudes. Those vertices become non-local. In flat space, they are non-local, right?
So I'm not sure that I understand, but BCFW is supposed to be like a general tool to compute amplitudes in local theories.
Yes.
Yeah, so if theory is non-local, it's not applicable. Yeah, so which just means that it is not going to work in this context, both in the AES case and also in flat space.
Other questions?
What is the difference between what you did and Baldessena-Pimentel?
Okay, so essentially they use Ponomarev coordinates, which, well, in a way breaks a Lorentz symmetry. So I want here, but here I want to keep Lorentz symmetry as a 3,1 minus. So for many people, it's more convenient to keep use Ponomarev coordinates, which means that SO3 remains manifest, but then you separate this as that Ponomarev coordinate. And then they do Fourier transform, which is these 3x coordinates, and they get somehow momentum representation next to the set. And then for this momentum representation, they use SO3 spinors. So essentially, their analysis is similar, but they don't have manifest SO3,1 covariance, they have manifest SO3 covariance. But for some reasons, this is useful, especially in the context of cosmology, where you don't deal only with DS, but with more general backgrounds like in Hilbert and Walker, you still have SO3 symmetry.
Other questions?
Sorry, you spoke about the representation of ISO SO13 of the Lorentz of the Poincare group, and you spoke about an orbit of dimension 2. Yeah, so of Kirillov dimension 2. I think that when SO typically what one does in the case of semi-direct semi-direct product, you take orbits on the R4 on this R13, and I think that normally they are of dimension 3. So I would like to ask you what it means dimension 2.
Yeah, so precisely the point is that for this construction, for holographic construction, we would need a representation of dimension 2. But if you do this standard analysis with induced representations, you indeed get orbits of points on the direction of SO3,1, which are either cones or hyperboloids, which are all 3-dimensional, not 4-dimensional. So, or you can also have the point at the origin, which is like 0-dimensional.
with
So you
the representation.
you see immediately that there is nothing suitable there.